Hello everyone, my name is Nidhi Gupta. I am assistant professor in engineering college, Ajay Kumar Garg Engineering College. Today we are going to discuss the data structure, another data structure of non-linear type, that is trees. So trees is a data structure having the non-linear order. So data is stored in non-linear order in case of trees. So let's start. So tree is a non-linear data structure which organizes the data in a hierarchical structure, and it is a recursive definition. A tree is a connected graph without any circuit. If in a graph there is only one path between every pair of vertices, that graph is called a tree. So a graph is a tree if it is minimally connected, having the minimum number of nodes, minimum number of edges, and it is minimally connected to each other. And a disconnected graph is never considered as a tree. So tree must be always connected in nature. Now the properties of tree. So the important properties of the tree data structures are: there is one and only one path between every pair of vertices in the tree. So as I have said that the tree is minimally connected, so any path from one node to another, there is only a single path. So then another is there is a tree with n vertices has exactly n minus 1 edges. So when it is minimally connected, in case you are having suppose 2 nodes, and in 2 nodes then there is only a single edge, then it means that it is a tree. So the 2 nodes must be having the single edge, just like as we can see over here. Suppose this is a node A and this is another node B. Okay, so we are having the n is equal to 2 over here because there are 2 nodes, and if they are connected, then minimally we can connect it like this. So over here the number of edges is equals to 1, so that is n minus 1. So this is a tree having 2 nodes. In case it would be a graph, then there may be more than 1 edges, maybe more than 1 edges, it may be having the self loop as well. So a graph is a tree if it is minimally connected to each other. So a graph is a tree, so any connected graph with n vertices has n minus edges in a tree, as we have discussed in this example. So this is the difference here. You can see the tree and a graph. So over here, this is a tree. The tree is having 1, 2, 3, 4, 5, 6, 7, 8. 8 number of nodes are there, starting from A to H. And we can see over here that there is only a single path from one node to another. Just like from the vertex A to the vertex F, there is only a single path, that from A we can move to C, from C we can move to F. Similarly, from any node to another, just like B to H, we can go from B to E, E to H. No other path is there. But in case of graph, there may be multiple paths. For example, from A to H, we can move from A to B, B to D, D to H. This is one of the path. Another path may be A to B, B to D, D to E, E to F, F to G, and G to H again. So we are having multiple paths in case of graph. So graph, of course, it is not minimally connected. So we can see over here also that the number of nodes are 8. So over here n is equals to 8, and over here the number of edges are 7. As we can see, 1, 2, 3, 4, 5, 6, 7. But in case of here, when n is equals to 8, the number of edges are 1, 2, 3, 4, 5, 6, 7, 8. It is 8. So E is equals to 8 over here. But over here, the n is equals to 8 and E is equals to 7. So we say that if the number of edges are n minus 1 and the graph is connected to each other, then we can say that it is a tree. And in case of graph, there are multiple edges. Parallel edges are always there. Even more edges we can also insert, just like over here, like this. This is a graph. This is a graph. So these all are, this is a graph having the multiple edges there and multiple paths from one node to another. But in case of trees, the tree is minimally connected graph. So let's proceed. So there are some basic terminologies of trees. Some of the important terminologies are just like what is a root, what is edge, parent node, child node, siblings, degree, internal node, leaf node, level, height, depth, subtree, forest. So these are some of the basic terminologies that we must be knowing before we proceed to any operation of the tree data structure. So the first and the most important basic term is the root. So root is a special node in a tree. So the first node of a tree is referred to as root. So in any tree, there must be only one root node, and the tree originates from the root node only. So if in case the tree is having only single node, then that node is only considered as a root. So we can never have multiple root nodes in a tree data structure. So over here, this is a tree, and this A, as the tree originates from the A, then A is known as root node. Next is the edge. The connecting link between any two nodes is called as edge, as we have discussed earlier. So in a tree with n number of nodes, there are exactly n minus 1 number of edges. Next is the parent. The parent node, the node which has branch from it to any other node, is called a parent. So a parent may have multiple child nodes. So a node which has one or more child nodes is called a parent. As we can see in the family relation also, there is a parent and there are multiple childs of the parent. So in the same way, over here also, tree also forms the hierarchical structure. So over here, the node A, in the last example, we can see that, for example, B is a parent of D, E, F. So D, E, F are the child nodes, and D, E, F are the child of parent node B. Similarly, G and H are the child nodes of parent C. Now, the child nodes, as it is quite clear that the node which is a descendant of some node is called a child node. So all the node except root node are the child nodes. So we have seen in the earlier examples the child nodes as well. Similarly, the child having the same parent is called the siblings. So in case any of the node, just like over here D, E, F, all D, E, F are having a same parent called B, and these D, E, F are the siblings. We say D, E, F are siblings. Similarly, G and H are the siblings of the parent and they are having a common parent called C. B and C are the siblings of parent A. I and J are the siblings of parent E. So this is sibling. Another is degree. Degree, there are two definitions. First is the degree of a node and second is the degree of a tree. Now the degree of the node is the total number of child nodes of that particular node. So total number of children is represented as a degree of that node. Similarly, the highest degree of a node among all the nodes in a tree is represented as the degree of the tree. Over here we can see the degree of G is 1. Over here the G is having a single child. So we say the degree of G is 1. Similarly, degree of E is 2. Degree of B is 3. because the B is having 3 number of child nodes, so degree of B is 3. Degree of A is 2. Now, among all these degree of a particular tree, what is the highest number of degree of any node having the highest degree is represented as a degree of a tree. So, over here we can say this tree is having the degree 3. So, degree of the tree is 3 because 3 is the highest degree of any node in this tree. Now, there is a concept of internal nodes. So, internal nodes, the nodes which has at least one child is called internal nodes, and the nodes which are not having any of the child are called leaf nodes. So, internal nodes are also called non-terminal nodes. So, every non-leaf node is a internal node, and the leaf nodes, it means the leaf nodes are those, we can say these are the terminal nodes which are not having any of the child nodes. So, leaf nodes are also called external nodes. So, let's see over here. So, we can say that I, J, K, H, D, I, J, K, H, D. These are called leaf nodes. Similarly, we can see this B, C, G, E, these are the internal nodes. So, we can say terminal, non-terminal. So, D, I, G, J, K, F, H are terminal nodes, and B, C, E, G, A, these are the non-terminal nodes. The next term is the level of a tree. In a tree, each step from top to bottom is called the level of a tree. The tree count always starts with 0. So, the level is always starts from 0 and its is incremented by 1 at every level. So, over here we know that the root is always the first node of a tree. So, the root is always considered at the level 0, and thereby at every level the count of level is incremented by 1. So, over here B and C are at level 1, D, E, F, G, H are at level 2, I, J, K are at level 3. So, in general, we can say that in the total number of the maximum number of nodes at level L is equals to 2 to the power of L. So, over here we can see 2 to the power of, over here it is the 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. Maximum number of nodes in case the tree is binary tree, then we can say that the number of nodes at the level L is 2 to the power of L. So, we will see this later. Next is the height. The height of the tree is the total number of edges that lies on the longest path from any leaf node to a particular node, and it is considered as the height of that node. So, for example, over here we can say this is the node B, and as we have seen the total number of edges that lies on the longest path from leaf node to the particular node. So, the leaf node over here is I is the leaf node. So, the length of the path is I to E1, E to B 2, again 1. So, 1 plus 1 2. So, over here from I to B it is the height 2. Similarly, from J to B it is height 2. Again, from K there is no height. So, in this case we used to say that the height of the B is 2 because there is a longest path is of 2. So, the height of B is 2, height of C is again 2. From K, K is a leaf node. So from K, the height of C is 2. From H, the height of C node is 1. So from 2 and 2 is the bigger number. So the longest path is 2. So height of the C is 2. Similarly, the height of H, as there is no child node, it is a leaf node. So it means that it is at the 0. So the height of the leaf node is always 0. So height of K is 0, height of F is 0, height of I, J, D is all 0. So height of all leaf nodes are 0. Now, another term is the height of the tree. The height of the tree is the height of the root. So as we know that the root is always at the maximum level if we see from the leaf node. So the height of the root node is considered as the height of the tree. So over here, starting from J, J to E, E to B, B to A, the height of the root is 3 over here. So the height of the tree is 3. Now, some of the key terms that we have discussed till now is the degree of a node, degree of a tree, path. So path is a sequence of consecutive edges from source node to the destination node. So we have seen in the earlier example also that from G to B, this is a path, G to E, E to B. So it is a consecutive edges, sequence of consecutive edges is considered as a path. Height of a node we discussed, height of a tree we have discussed, depth of a tree now. So depth, height we always considered from the leaf node to a particular node, and in case of depth, it is the maximum level of any node. We can say the maximum level of any node is the depth of that node. So maximum level means we start from the root and we go to that particular node for which we want to find the depth. So over here we can see that in case of F, the depth is from A to B, B to F. The depth is F, the depth of a particular node. In case we talk of the depth of a tree, then in that case, it is the longest path from root node to the leaf node. So over here, as we know, these all are the leaf nodes. So from A to F leaf node, the path is 2. Similarly, from A to leaf node J, the path is 3. And similarly, we can see from A to I, it is 3. From A to K, again it is 3. And from A to H, it is 2. So the maximum, the highest number is 3. So that is why we consider that the depth of the tree is 3. So this is the difference between the height and the depth. In case of height, we start from bottom to up, from leaf node to the particular node, and in case of depth, we start from root node to that node. Now, as we have discussed, the depth of a node, depth of a tree. Now, depth of a root node. So, as we know, the depth is counted from the root node only. So, in this case, the depth of the root node is always 0. So, this figure is showing the differences. You can see different depth of different nodes. Just like A is a root node. The depth of node A is 0. Depth of node B is 1. C is again it is 1. And D is 2. Depth of E is 2. F is 2. G is 2. H is 2 again. And I is 3, J is 3, K is 3. So, the depth of the tree is 3. Next is the concept of subtree. As we see that a tree and a subtree. The subtree is a part of tree only. So, in a tree, each child from a node forms a subtree recursively. Every child node forms a subtree of its parent node. So over here we can see A is the root node, and we can say that A is having the 2 childs, and over here these are the 2 childs. So we say that the tree which is starting from B and all the descendants of B, this all forms again a tree. So this is called a subtree. So it is starting from B. So B is acting as a root node for this subtree, and D, E, F are the childs of B, and again I and J are the child of E. Similarly, so this subtree is also referred to as subtree. So the root of this subtree is C. So that is why we always say that tree is recursive, because as we can see, this whole tree, the whole tree is having the root A and it is having some child nodes. Similarly, over here the B is the root and it is having the again subtrees, just like this is a subtree. This is again a subtree. The root node is E over here for this subtree, and this is again a subtree having the single node. Over here we can see, oh, this is again a subtree having the root C. This is again a subtree. So it is a recursive. So that is why we say in a tree each child forms a node and a node forms a subtree recursively. Now the forest. So the forest is a set of disjoint trees. So over here we can see, as we have seen, this is a tree, and again this is also a tree, and this is disconnected. So this disjoint trees are considered as a forest. In case there is a connection between these two, for example like this, there is an edge, then this forest becomes the tree. So any connection would lead to the tree. But over here, when it is disconnected, the components of the tree are disconnected, we considered it as a forest of that tree. Now, we start with the spatial trees called the binary trees. So up till now, the tree may be having the 0 child, 1 child, 2 child, 3 child, n number of childs may be there. So when that we called some spatial trees having only at most 2 child, then we considered those trees as binary tree. So a binary tree is a tree in which no node have more than 2 child nodes. So consider this tree over here. We can see that the maximum number of child of any node is 2. So this is a binary tree. So it means that 0, 1, 2 all are permissible, but more than 2 is not permissible. So over here, as we see that this is a binary tree having the root node A, and this is again left subtree, this is right subtree, and this subtree is again having a root, and it is all recursive. So over here we can see that B is a left child. So when we have the binary tree, only 2 childs are there maximum, then we consider it as a left and right. So B is the left child of A and C is the right child of A. Similarly, this subtree is considered as a left subtree of A and this subtree is considered as a right subtree of A. Now, we say that A is a father of B and C, and the B and C are the siblings. Node D, H, I, F, J, these are the leaf nodes as we discussed. Now, a binary tree T is either empty or such that T has a spatial node called a root node. So, this is the formal definition of the binary tree. So, the tree T has a spatial node called the root node. The T has 2 set of nodes we considered as LT, that is left, and RT means right subtree. So, left subtree and right subtree of T respectively, and LT and RT are again the binary tree. So, we say that the binary tree may be having 1 node, it may be empty, it may be having single node, it may be having 2 nodes, it may be having 2 subtrees, LT and RT, and these LT and RT itself is a tree. It is itself a binary tree. So this is all recursive. So we can see over here binary tree with 2 nodes A and B, binary tree with 2 nodes again A and C, B is not there. It is only having the right child and left child is null, nothing is there. Over here binary nodes with 3 binary tree with 3 nodes. A is a root, B is left and C is right. So either of them may be left or right may be null also. So a binary tree is a finite set of elements that is either empty or is partitioned into 3 disjoint subsets. The first subset contains a single element called the root of the tree. The other 2 subsets are themselves binary tree called left and right subtree of the original tree, as we have discussed over here. This is one set, this is another set, and this is another set. These 3 subsets are there. A left or right subtree may be empty. Each element of a binary tree is called node of a tree. So this is a figure which is showing all these that I have discussed so far, that this is a root node, this is a left subtree and this is a right subtree. So the left subtree of the root node, which is denoted by LA, is the set LA B D E F, B D E F. So this is B D E G, sorry. So this is the left subtree and right subtree is CFG, CFH. Now let's discuss that how this binary tree is represented in the data structure. So we see that the representation of binary trees. Now, in case of memory representation, we represent this binary trees in 2 ways. The first is array representation and the second is linked list. These 2 ways are there to represent the binary tree. For example, I am having a binary tree A, B, C and maybe D. Now, in case of arrays, we represent this in the form of a matrix. This matrix is called, so in the form of the arrays 1D array. So over here, suppose this is a 1D array. Okay. So this root will always take the first position and thereafter the left child will take the second position, then right child will take the third position and so on. So in general, we say that if the index starts from 0, the first position is taken by A, then B, then C and then D, and in case over here there is any element, then that would be stored over here, but there is no, this would be empty. So 1, 2, 3, 4, 5, 6. So in total, so there are 7 elements inside this array. The root always take the kth position, kth index number. So this kth position is always occupied by the root node and this left node occupies the 2 into kth position. And this right node always occupy 2k plus 1 position. As we can see over here, since A is at the position number 1, then its left node is at 2 into 1, that is first. If this k is at the position k, so this left is at 2 into 1, that is second position. So this is first position, this is second position, this is third position, and this right child is 2k plus 1, that is 2 into 1 is 2 plus 1. So when k is equals to 1, because over here this is the position. Position and index are different in my case. In case my index number starts from 1, then we can replace it by the index number also. Over here also we can see if B is at the kth position, then D would be at 2k position. So the position of B is like 1. So the position of D would be 2 into 1. So over here, sorry, the position of B is 2 over here, then the position of D is 2 into 2, 4. So we can see like this, that the D will be stored at the position number 4. This is the position number 4. So this is the position number, and accordingly the data is stored according to the position numbers. So it means that all in all, in case of array, if the parent stored at k, then left child stores as 2k and right child stores at 2k plus 1 position. So this forms the array representation of binary trees. So let's discuss the linked representation of binary trees. Now, in case of linked representation, suppose I am having the array, I am having the binary tree this is the binary tree I am having. Now, in case of linked list, each of the element, each of the node is represented as a node of a linked list. So in linked list, the node is represented as the data, and we know that in case of binary tree there are at most 2 child. So this is considered as a pointer for the left child, and this is considered as a pointer for right child. So this is the structure of a node in the linked representation of trees. So this data represents over here, let's we say that if we want to store this A, so over here this A is considered as a data, and we have the two child, so it stores the addresses of B left child and address of C will stored at the right child. So this tree is represented as, there is a node A, okay, and then over here this is again a node with B data. Over here at the right child we are having the C data is stored, and in the right of the C there is a D data structure. So we can see that those which are left empty is considered as a null pointer. This is null, this is null, this is null. Again these are null pointers. So this is the linked list representation of binary tree, this binary tree. And of course there is a special pointer called root which points to the root node of the binary tree. So this is the binary tree which is having the root as this node and B, C, D. So in case of arrays, we store the data, we occupy the maximum number of nodes of that particular level, and then accordingly we store the data. In case of linked list, it is space efficient because no extra data is being stored, no extra space is being occupied. As we are having only 4 nodes, then we are occupying only 4 nodes, and we store this data like this. Now, like any other data structures, we can perform many operations on the trees as well. For example, the operations that we can go for is, the first is traversing. So this traversing involves many things, just like searching for an element, visiting each element, counting the number of nodes. So all these operations we can do while doing the traversing part. The second is, we can insert any of the element inside the binary tree. This is one of the operation. Next is deletion. We can perform the deletion as well. We can delete any element from the tree. In that case, we need to consider that what we are deleting, whether we are deleting the node having some child nodes or not. If it is a leaf node, then it's all okay. We can delete it directly. Otherwise, in case we are having some child nodes, so its descendant must be get some place so that they could be connected to the remaining node. So for this, we need to all take care when we go for the deletion. So these are all the primitive operations that we can perform on these tree data structure. So these operations can be performed in case of array representation as well as in case of linked list representation. So in the next lecture, we will be seeing how we can go for the operations of any binary data structure. Thank you.